everybody. So as you can see, we're going to talk about the atom today, and now you can actually see my face. I got some new software that allows me to, you know, record the iPad and also my webcam at the same time. So now you know that I'm looking at you, and you have to pay attention. We're going to talk about, in the beginning of this PowerPoint, the history of the atom, the discoveries that you learned about last year. I'm going to go really quickly through this because honestly, you should kind of know this stuff already. I'm just going to lay it out there for you. It's your responsibility to know it. We did it last year, and we even did quantum mechanics last year, but I am going to spend more time going more slowly through that. So the first part of this chapter is dedicated to the actual history of the atom. Into it, let's do some of the background information about the atom, and hopefully that will, help you to, help refresh your memory. So, the first thing I want to talk to you about is, sort of what we know today about the atom. And, we know things like all the atoms have these three subatomic particles. We have protons, neutrons, electrons. Hydrogen, it is the simplest of all the atoms. It is one proton, one electron, so it doesn't have that neutron, unless it's one of the isotopes of hydrogen that we'll talk about. The radius of an atom is really, really small. It's about 1 angstrom, or 10 to the negative 10 meters. Atoms, they're mostly made up of empty space. We know the electron is really, really small, and because of this, because the electron is really, really small, it doesn't occupy much space in the electron clouds. Most of the atoms are empty space. Also, the electrons are found in energy levels. If you're looking at it from the Bohr model point of view, which we know really isn't true, the electrons are in these orbits, but in reality they're actually in orbitals. So, when we look back at, who first discovered the atom, we sort of, give credit to the Greek philosopher Democritus, and his idea that, you have these indivisible tiny units, which he actually called, atomos, which is Greek for atom. But when we start looking into it, you see that other cultures have the same kind of idea. And so we can see that, a lot of historians, they've actually discovered that, there was this idea of an atom that was proposed on the Indian subcontinent, so in India in that area. We also see that, when Europe was in the Dark Ages, there was sort of this resurgence of science in Asian cultures. So it's interesting, from our point of view, we always kind of tell the same story. In reality, it turns out that there were other cultures that were interested in science, that were discovering, atoms and thinking about what they meant at the same time. Now, the first scientist of real significance that we're going to talk about is actually John Dalton. And John Dalton had proposed his idea of the atomic theory. And, we've heard this before. They're made up of tiny atoms. They can't be divided. They're indivisible. They all are exactly alike if they're the same element. And you can join them together to form these compound or these complex elements, which we know as compounds. So, Dalton, his idea of the atomic theory was really the first scientific theory that we had regarding atoms. But, his model was sort of very simple. So there's evidence, that came out soon after his discovery of, what an atom is and the basic idea of it, and evidence suggesting that there were subatomic particles. And one of these pieces of evidence came from J.J. Thomson. And I'll do this in class for you, J.J. Thomson's experiment with the cathode ray tube. I'll show you what a cathode ray tube looks like. I'll give you an idea of, what the beam of electrons looks like when it's when we put a magnetic field around it. So you can see for yourself, this is what a beam of electrons looks like coming from the cathode in a cathode ray tube. But there's also another scientist who we didn't really talk about much last year, and that was Robert Millikan. And Robert Millikan's experiment, called the oil drop experiment, what he was really able to do with this experiment was charge oil droplets. And when he did this, he saw that they all had multiples of this fundamental charge. And that fundamental charge was 1.6 times 10 to the negative 19 coulombs. And this fundamental charge is the charge of an electron. And his simple experiment actually holds true today. We see that even today that an electron has the same charge. Now, J.J. Thomson, he had actually discovered a charge to mass ratio. And so putting together the charge of the electron that Millikan discovered and J.J. Thomson's charge to mass ratio, they were able together to discover what the actual mass of an electron was. And we know a mass of an electron is really, really tiny. It's 9.11 times 10 to the negative 28 grams. And this is about 1/1836 the mass of a proton or a neutron. So those are the first subatomic particles that were discovered. But as we look at J.J. Thomson's model. J.J. Thomson had a model of the atom where he knew that there was a negative particle in it. Like he knew that, for example, there were positive and negatives, and he called this plum pudding. But what he didn't know was he didn't really know the arrangement of those subatomic particles in the atom. And that came from Ernest Rutherford. And he had his famous experiment, his gold foil experiment. And this one really, even on the AP and on the IB exam, they still ask about it. And so you should know that, most of the particles, those alpha particles, they pass directly through. There was no deflection. They weren't hitting anything. I told them that the atom was mostly empty space. And at the same time, though, some of these particles, they were hitting something that was much, much more massive and positively charged compared to the alpha particle. And it was being deflected at either a large angle or a small angle. And so that gave him the idea that, you had a positive nucleus, and then you had the electron somewhere around the nucleus. Now, this was a very quick, run through of the history. And today we know that, there's these three subatomic particles. We know the mass of a proton to be this many grams. Like I said, the mass of an electron is about 1/1836 of that. And we know that the charge of an electron and a proton have this 1.6 times 10 to the negative 19 coulombs. If we look at a relative mass type scale, where we're talking about AMUs, the proton and the neutrons, those are about 1 AMU, and the electron is about 2,000 times smaller. When we look at the relative charges, we can see positive 1 for a proton, neutral for a neutron, negative for an electron. When we look at the periodic table, it's also important that you're able to actually figure out, how many protons, neutrons, electrons there are. And all of you are pretty good at this. But just to review it, your IB table has the atomic number up top, and they call it Z. And then it has the symbol, the name, which they don't give you on the actual table, and also the atomic mass, which is the average atomic mass. And that, you should know that the atomic number, that this is the number of protons. And you should know that the number of electrons is equal to the number of protons in an atom, but if we have an ion, it's obviously not going to be the case. And then you could find the neutrons from subtracting the mass number from the atomic number. Now we could also have an ion as well, and an ion is going to have a charge to it. This diagram, you'll notice it's a little bit different than what you saw on the previous slide. This is what we find in the periodic table, but a lot of times they'll note it where they put the mass number up top, and they'll put the atomic number on the bottom on the left of the actual element symbol. So for example, I could do like, nitrogen 16, put the 7 there, and I could put the charge over here, -3. You should be able to find protons, neutrons, electrons by using this symbol or by using the periodic table, and we're going to go through how to do that in class. Here are some examples for you to look over, though, in the meantime. We have, beryllium, the notation, the 4 on the bottom tells you the atomic number. Therefore, it tells you the number of protons. The mass number is 9, so if we do 9 minus 4, we'll get the neutrons. Since it's an atom, the protons and the electrons, are equal to each other. If we look at calcium 20, the atomic number is 20. The mass number is 40. That means that we have 20 protons. 40 minus 20 will give us the 20 neutrons. It's a +2 charge, so it's lost 2 electrons, and because of that it now has a charge of +2, and it only has 18 electrons. We'll practice a bunch of these in class just to make sure people remember them. If you're good with them, we'll move on. The last thing I want to talk to you about in this particular video are isotopes. So when you have an isotope, it's the same number of protons, it's the same element, but it has a different number of neutrons, and you reflect that in the mass number. So here are the isotopes of hydrogen. We have protium, we have deuterium, and we have tritium. They all have the same number of protons and electrons, but the neutrons are different for each of them. You should know the names of these particular isotopes, and you should know that isotopes have different number of neutrons. Here they give you another example with carbon. And in any sample of carbon or hydrogen or any naturally occurring element, you are going to have the situation where you will have all of these isotopes with a certain amount, a certain percentage or abundance. One of the skills you need to know how to do is calculate the actual average atomic mass. And so here's another example with chlorine, and here's how you would calculate the average atomic mass. So to do this, you would take the percentage times the mass, and you would add it to the next percentage times the mass. And then you would divide it by the total percentage, or 100. You could change the percent to a decimal and do that. If you had me for honors chemistry, I used to call this getting mad, M-A-D, because I would multiply, I would add the answers, and then I would divide by 100. Notice this is a weighted average. It's not 35 plus 37 divided by 2. It's the 35 times its percentage, plus the 37 times its percentage over 100. Now I'm going to stop here for this video. Next time we'll do mass spec. Thanks so much for watching me.